I think we can start. Good morning, everyone. Welcome to this environment session. We had the plenary yesterday. We are continuing now with the parallel sessions on environment. We have 4 speakers today, and then we will have the panel discussion. So it's a pleasure for me to invite the first speaker today, is Gary Miller, Vice Dean for Research, Strategy and Innovation, Professor of the Environmental Health Science, Mailman School of Public Health, Columbia University, New York, USA. Thank you. The floor is yours.
Thank you for the organizers for the opportunity to present some of our work. See if the slides come up here. So I'd like to take time to talk about this concept of the exposome or exposomics. And the idea here is we're trying to measure the complex environmental drivers of human disease. And I think we want to start here when we think about what our phenotype, who we are as people, is that it's a result of the combinations of our genes and environment. We learned this way back in biology class in grade school. And if you look at the progress over the past century or more on the genetic side, we've made extraordinary gains on this, where going back, they're actually at the Mendel Museum, where the work done here in Brno with early genetics all the way through to the Human Genome Project, and now the ability to get very deep sequencing done for just hundreds of dollars. We have studies with hundreds of thousands of people that have full genome sequences done. But if you look at that equation of gene by environment, I draw that E very small, because we've had this extraordinary advances on the genetic side, but we haven't had a comprehensive analysis of the environmental drivers of disease. And I think that's why Darwin looks a little sad in that picture, because he knows that natural selection was important and the environmental factors played a role. And this is where this idea of the exposome came up. So Chris Wild, who is the director of the International Agency for Research on Cancer at World Health, and was an environmental epidemiologist, was seeing these advances in genomics and thought, hey, we need to have this sort of complementary effect on the environmental side. And so he coined this term exposome and defined it as all exposures from conception onwards, including those from lifestyle, diet, and the environment. And people have kind of abbreviated this to be the totality of one's exposures throughout their life. And this was, when I first learned about this seemed a bit challenging, because how can you possibly categorize everything we're exposed to throughout our lifespan? It seemed like a very difficult task. And so a few years ago, Dean Jones and I were looking at how to really operationalize this concept of exposomics. And so we proposed this modified definition of being the cumulative measure, things we can actually measure, of the environmental influences and corresponding biological responses throughout the lifespan. And so the challenge here is that we might be exposed to some chemicals that are transient, they've left our body, but they left an epigenetic mark on us, and that is affecting our health downstream. So you have to look at how it affects the biology and not just the simple exposures. But if you link those two together, you can start building this story. So the idea is we measure what we can measure. We measure persistent chemicals that still remain in our body. We look at the short-lived chemicals that may reflect recent exposures, and these various biological responses, protein modifications, epigenetic marks, whatever those would be, like looking for those fingerprints of past exposures. And so the idea here is that we're really looking at this very comprehensive way. We're going to look at all these environmental chemicals, pharmaceutical chemicals, the drugs that are prescribed by our physicians, things like flame retardants, pesticides, all these chemicals that we're being bombarded by every day, but also thinking about our ecosystems, our access to green space or blue space, the socioeconomic factors, all these different things that are surrounding us, temperature, humidity, all of these external forces are playing a role in our health. And when we think about our changing climate, I like to think about it as being a force multiplier, is that as our climate changes, it accelerates all of these things. It changes our exposures to pesticides, You have various vectors that can spread diseases. It's changing the dynamics of that. And so climate change becomes very important because it's making alterations to all of these things. It's disrupting the balance. But to me, one of the most important things to think about is for these external forces to have an effect on our health, they have to change our biology. This idea is that just because the chemicals are there, just because these external forces are changing, if they're affecting our health, there has to be a biological signal. And so this idea of looking for those internal biological signals is as important as looking at those environmental factors. Because if they're not changing our biology, they are unlikely to affect our health, at least in a direct way. And so what we developed over the last decade or so is really working to measure as many of these factors as we can in a systematic way. And so this is just the approach that we have taken with my colleagues before when I was at Emory University in Atlanta, now at Columbia University in New York, is using mass spectrometry to measure as much as we can in a drop of blood. And the techniques have advanced so much over the last 50 years where 50 years ago we could measure 20 amino acids at a time. Now we have these chromatographs of hundreds of thousands of features that we can pull out of a drop of blood. And if we use different combinations of mass spectrometry, liquid chromatography, and gas chromatography, we can get incredible coverage of chemical space, and we can measure pesticides, things even like DDT metabolites, dioxins, flame retardants. We can measure all of these things in individual runs of biochemistry. And so the idea is that if we can capture all this information in a systematic way, we're not just looking at pesticides, just looking at flame retardants. We're trying to take an unbiased view and really measuring whatever sort of xenobiotics or chemicals are out there. And one of the challenges, though, is that when we look at all of these peaks, we really only know what a very small portion, less than 10% of them are. Many of these are unidentified. And one of the challenges for this is that in analytical chemistry, we like to have authentic standards. So if you're trying to measure the presence of a particular pesticide, you order the pesticide, you run it as a standard, and you know exactly what it looks like on the mass spec. But when you think about what compounds may be affecting us, imagine if you're exposed to a pesticide through your diet, and the microbes in your gut metabolize it, and now you have a microbial metabolite of that pesticide. I can tell you there's not an authentic standard for that. And so there will be this peak that looks like the pesticide, but it's a little bit different. And we sit there and say, well, we don't really know what it is. And so the analytical chemist says, we don't know what it is, we can't act on it. But in reality, we do know a lot about what it is, and we have to work on characterizing that. And I think here's a challenge where if we let perfect being the enemy of the good, if we're always looking at that highest level identification, we will ignore things that probably play a big role in human health. And so an example of this is one of the scales we use to identify this called the Szymanski scale. We want to get this level 1 identification where we have authentic standards and we know exactly what it is. But as I said, we often don't have this. And I like to compare this to what we see, for example, if you're identifying an automobile. Is our level 5 standard of just knowing what the mass to charge ratio is like saying I see a blue sedan or a pickup truck. As you go up, you get more information. You might have the make and model of the vehicle. You may even get to the level of having a license plate. And in that vehicle identification number is that level 1 standard. And imagine if someone robbed your house and was driving away and you saw the first 4 digits of their license plate. If the police officer came to you and said, do you have any information, would you say, well, I didn't get the entire license plate, so I have nothing to tell you? Of course not. You would tell them the information you had. I saw a blue car. These were the first 4 digits of the license plate. And that's enough information for that police officer to narrow down the search. And that's what we're trying to do with this sort of exposomic approach, is narrowing down the search to the point where we can see these things and work harder on actually figuring out exactly what they are. But it's okay not to know exactly what it is during the process. And so one of the examples of what we were trying to do to see how we could identify some of these unknowns is we went through and just systematically, we took liver fractions and put them in 96 well trays in the laboratory and would put known parent compounds into those wells and then use mass spec to measure the features that were there over time. So at time 0, you should see the parent compound. You wait an hour, you start seeing metabolites of it, and you can go through that process. You know it could only come from what you put in that vessel. So if you see a metabolite of one of those parent compounds, we can now put those into the databases and say, this is a metabolite of this sort of compound. And in this example on the right, we actually identified a metabolite of caffeine that no one had ever seen before. And we went through a stable isotope labeling and showed that it was a metabolite of caffeine. So caffeine's been studied a lot. It's a very popular molecule to study for many reasons. And the idea that people didn't know some of these metabolites is because they were only looking at the sort of textbook metabolites of it. And if you take the sort of unbiased approach, you can find these new things. Just imagine now if you look at, we have 80,000 chemicals in production in the United States. I mean, there's hundreds of thousands of these things out there, and we need to systematically get better at measuring these things in the human body. And so this brings us to this, our IRENE infrastructure, which is why I'm in Brno this week. Jana Klanova here is directing this. I had the great fortune as a US partner into this infrastructure, but this has 20 partners across Europe and the sole one here in the US at Columbia. And the idea here was when you looked at the infrastructures in Europe, there really wasn't anything there to help characterize how chemicals affect human health. And this is where we saw this opportunity to build up this infrastructure because we have to systematically do this. And so this has been what we've been working on earlier this week, talking about this, is how do we build the infrastructure to do exposomics? As you can imagine, when I'm talking about tens of thousands or hundreds of thousands of chemicals, the bioinformatic and computational challenges are extraordinary. We're looking at biological samples that may be kept in various biobanks, and so partnerships with various biobanks, and doing all sorts of analysis on these environmental exposures and what these sources are of these different chemicals we're being exposed to. And so the idea here was using this infrastructure to help build the infrastructure we needed for exposomics. And the idea here is we want to do studies like this. And so this is an example of a study we did with the Mayo Clinic in the US, where they were studying a liver disease that they'd done the genetics on it and could only explain about 7% of the variability. They didn't know who was going to progress to needing a liver transplant, which is the only treatment for this disease called primary sclerosing cholangitis. And so what we did was we ran our liquid chromatography and gas chromatography mass spectrometry on these participants and could identify many different environmental chemicals that were disrupting their endogenous biology. And one example we had early on was we saw this very specific disruption in bile acid metabolism. And when I first presented it to them, I said, well, obviously you're going to expect these disruptions for a liver disease. And they said, well, not really, because the samples we gave you, they were kind of in a dormant state of the disease. Their clinical chemistry was normal. And from that, they went back and did a very detailed analysis of bile acids and showed that they found novel biomarkers of disease progression because of what we found in our untargeted analysis. In our unbiased analysis of looking at all the different chemicals, we gave them new insight into this. We also found many different environmental chemicals that were disrupting various biological pathways. And now what we did with this was got preliminary data to get a very large grant from the National Institutes of Health, where we've increased the N from 40 patients per group to 800 patients per group. And so it took this very important partnership with this clinical population at the Mayo Clinic, but now we can do this this environmental-wide, exposome-wide association study in this. And exciting is that the precision medicine, the individualizing medicine program at the Mayo Clinic this year is holding their annual conference, and it's on the exposome. And so, for many years, we've had such a hard time getting clinicians to think about the environment, and here the Mayo Clinic is hosting a meeting focusing on the use of exposomics in clinical medicine. Another example, we've been looking at diseases like Alzheimer's disease and Parkinson's disease. In some of our untargeted approaches, we identified some environmental chemicals like metabolites of the pesticide DDT, which actually had been linked to Alzheimer's before, but we were doing it in this untargeted, unbiased way. We were looking for whatever we could find. And now we've working on another cohort where we have over 3,000 participants in it. It's a longitudinal design. We have several hundred incident cases of Alzheimer's that occurred during the course of the study. And so we have samples from before they were diagnosed, and we're going through and doing this exposomic analysis and finding, in some of this preliminary analysis I was looking at last week, my postdoc gave me a list of these chemicals, and I looked them up, and they weren't in PubMed. There was no paper that described them, but they were in PubChem. So they're chemicals that have been described, but they've never been associated with any human biology at all. And again, this idea is it's fantastic for discovery because you're totally opening up the search window by looking for whatever's coming off that mass spec without any a priori knowledge of what those chemicals may be. And so this study is underway. And then lastly, in thinking about sort of mechanistic studies is, my background is in toxicology. I like to look at these sort of gene-environment interactions, is we can bring all of this back into the laboratory, and we use C. elegans, and we can look at modifications in genes. For example, on the one side, we looked at a gene we thought was involved in Parkinson's. We could do RNA-seq, our high-resolution mass spectrometry, and link those two together. And then after this Alzheimer's finding we had, we took the C. elegans worms, put the human mutations of the genes involved in Alzheimer's, exposed the worms to the DDT pesticide, and looked at that gene-environment interaction and saw how it was disrupting the various biological pathways thought to be affected in the disease. And so the idea is it can really help guide our toxicology because we're taking this unbiased and systematic view of all these complex environmental exposures we have. And so now, what we want to try to do is do this for many different diseases. If you have a longitudinal study of any disease and you've biobanked those samples, we can go through and do this mass spectrometry. And if you've geocoded those samples, we can use geospatial data to look at the various environmental patterns and link those two things together. And we've actually done this with air pollution in our Alzheimer's studies and really linked the complex environmental to these complex internal markers of changes in biology. One exciting project kind of getting underway here in the United States is the All of Us program. So this is a very large cohort, maybe similar to UK Biobank, trying to enroll over 1 million participants. And they've recently put out a call about integrating the environment more into All of Us. And so we're trying to position ourselves to say, we can do this exposomics in this sort of study. But one of the questions they ask is, how do you scale this up to 500,000 people or 1 million people? And so that's one of our challenges now is really increasing our speed and efficiency. And with that, I'd like to thank the people that I've worked with over the time. We've started a new journal called Exposome, published by Oxford University Press, and we teach a boot camp every summer at Columbia, and I've written a couple books on the exposome if you want to learn more. So with that, thank you.
Thank you, Gary. It's working? Yeah. Okay, so now I invite the second speaker, Benoît PIRENNE, Director of User Engagement Oceans Network Canada. This is an initiative at the University of Victoria, British Columbia, Canada. Thank you.
Thank you, Gelsomina. So as Gary just told us about, scaling up returns on the science investment through research infrastructure and new technologies, what I'm going to talk about here is not in the framework of the health sciences, but more in the natural sciences, and particularly in the exploration and understanding of the oceans. So what I'm going to talk about is Ocean Networks Canada. What I'm going to talk about is the Ocean Networks Canada is basically an observatory system that looks at the seabed, the water column, what's under the seabed, and everything to do with the ocean. And the ocean, as you may know, is not just the combination of water and whales and fish. It is a lot more going on, in particular when you think about the climate, the exchange between the atmosphere and the ocean, as well as the life that you find in there. But there's also the subsea, and the subsea is all the geology, the tectonic plates and everything that happens when they slide underneath other tectonic plates, subduction zones, rifts, and other generation of hot vents and whatnot. So that's what we wanted to do, is basically using an observing system with real-time data, cabled systems with power and electricity, and communication capabilities, basically return all that data back to shore. And so OceanWorks Canada now has a number of observatories around the country, and you see a bunch of names on the map here, where we have basically installed equipment that's directly connected to the rest of the world. So OceanWorks Canada is a research infrastructure with over 160 staff, representing $500 million of investment to date. We have more than 1 petabyte of data so far, and we think that together with our friends south of the border in the US, with the Ocean Observatory Initiative, we're kind of world leading in this particular area. But whereas all the flashy bits of the stuff that we do have to do with basically installing equipment, getting famous imagery from the seabed, the product that we deliver is data. And in fact, 30% of the staff and of the 160 that I mentioned are really devoted to all aspects of the data management that all the sensors that we have produce. And to reflect that importance as well, we have become a member of the International Council for Science World Data System, and I think our colleague here is in the room from the World Data System. We also participate in data interoperability initiatives and also several United Nations as Sustainable Development Goals 14 and a bunch of projects therein. We're collecting data from over 9,000 sensors distributed across the seabed, in the water column, above the water, under the seabed, and around the country. We provide data in an open way, so basically 99% of our data is immediately available to anyone. And we also want to deliver products, and I'll come to that in a minute, and I mentioned the size. But what's important to note, and when you build a research infrastructure and you need to refresh it from time to time, is to have a good strategic plan that adapts your objectives to the questions and the challenges of the day. And so here, I'm not expecting you to read any of this, but the big words here are what's important. The three main goals of our new strategic plan have to do with continuing to support the observation of our oceans, in particular for science. The second frame is the societal benefits that can be derived from the measurements that we do, and essentially basically how we benefit the society through governments and industry and so on. And finally, the third aspect of our strategic plan now has to do with climate mitigation solutions, or how do we benefit the planet? So benefiting science, society, and the planet as a whole are the three areas that we want to cover. And then I'm going to go through, a few examples as we move forward. So essentially, our science support mission is to offer continuous real-time data about the ocean. Sorry, that was converted from Keynote and didn't do a good job. Support of experiments. So basically collecting data on core essential ocean variables is one thing, but of course supporting experiments is another one. And of course encouraging multi and transdisciplinarity is one of our objectives as well from the science side. So what we do again is a more detailed view of some of the map that I've shown before, with details as to how we connect those instruments together, but I'm not going to dwell on that. We have been measuring essential ocean variables on the west coast of Canada already for 16 years at 1 Hertz frequency, so you can imagine they represent a large amount of measurements. And the plot underneath represents just 4 of those variables at 1 location for this period of time. And then in terms of augmenting the interest that the observatory and the facility produces. So it's not just about marine biology, oceanography, or other geology. It's also now of interest to astronomers and high-energy physicists who wants them to install a neutrino experiment underwater. It would be a very large system. But let's move on to societal benefits now. What we want to do is to provide data products that support decision-making for government and industry. And I'm going to cite a couple examples of that momentarily, and also supporting indigenous communities by providing a meaningful engagement with them. Again, sorry for the missing bits, by empowering them. The first of the support of the public, essentially, and the industry is to provide earthquake early warning. I showed earlier in the second or third slide that the region where we install our observatory is pretty much prone to the effect of a subducting tectonic plate, i.e., also known as earthquake prone. So we live in an earthquake prone zone where a megathrust earthquake could occur anytime. So earthquake early warning, even if it produces only 60 seconds of warning, is important. We also provide to First Nation communities or indigenous communities, as well as municipalities on the coastline, the ability to provide tsunami impact simulations. So we run very complicated wave models that are running on a digital elevation model, and we're providing essentially what amounts to a simulation of what could happen if an earthquake were to provoke a tsunami offshore that would then have an impact on low-lying lands nearby. We also offer another tool, another data product that could be helpful for search and rescue at sea. So essentially sea surface measurements. So if you have a lost cargo, man overboard situation, or oil spill, rather than searching in the middle of the night in a radius of 360 degrees, you can then narrow down to a cone that would accelerate your search and increase your probability of finding the missing bits as soon as possible. Governments are establishing marine protected areas around the world, and in particular Canada has promised to increase its own marine protected areas by a large amount in the next few years. And so a zone here that happens to be superimposed over our observatory is an area of interest, as they call it. And so what we can provide here is help the government and therefore society in monitoring marine protected areas. And finally, with our program Community Fishers here, we're empowering indigenous communities to collect data about their own environment, creating a baseline of measurements that will help them in case of changes in this environment to understand whether the change is natural or maybe anthropogenic in nature and whatnot. And finally, helping the planet, so climate solutions. What we want to do is actively support ocean-based climate mitigation research and demonstration. So of course, as you know now, not only do we have to stop burning fossil fuels, we also have to start thinking seriously about removing CO2 from the atmosphere and from our activities such that we can bring back the situation to a point where we can essentially still allow our civilization to progress. So the way we can do that is by supporting experiments that are happening a little bit all over the world now to enhance alkalinity of the ocean such that the ocean can then take in more CO2. Some people are thinking about growing kelp, have kelp farms, harvesting the kelp, putting it in bundles and dumping into the seabed where it hopefully will stay for a long time, or geological storage. So we have at ONC, together with colleagues at different universities, including Columbia University, an experiment in geological storage that would provide essentially permanent storage of CO2. And that's the project which we call solid carbon, which would basically consider not only capturing CO2 from the air, but also re-injecting it directly in the seabed, under the seabed, under the sediment layer, in the basalt being porous And if you inject CO2 in it, it will, as has been demonstrated in Iceland, turn into rock, essentially, within a few years. And I think I'll stop here.
Thank you. We will have all the questions later on in the discussion, so I invite the third speaker, Nicolaus HANOWSKI. I hope I pronounced it well, Head of the Earth Observation and Missions Management and Ground Segments Department from the European Space Agency. The floor is yours.
Yeah, good morning, ladies and gentlemen. Great pleasure to be here. My first reflex is to thank the organizers for inviting me to participate in a meeting which is unusual in a way that I try to find the context in medicine, ocean science, and being immediately successful in doing so. There is immediate recognition and inspiration from understanding how other disciplines are looking at the changes of infrastructure and methodologies in order to reflect on the impact of environment and our understanding of the environment. And that's exactly the topic that I will try to address as well. So I'm delighted that this connection can be made so easily. First of all, let me say my role in the European Space Agency is I'm responsible for all the satellites in Earth observation that we are operating. We are operating a large fleet, and I have a slide that is just showing the infrastructure, if I may say so, that is the one that I'm relating to. This is the European Earth observation mission fleet, if you want. The institutional part of it I need to emphasize, and it consists of three elements: the science missions with new technologies, cutting-edge instrumentation to understand the Earth, the Copernicus program, which is an EU program in which we are contributing, the European Space Agency is contributing budget to the build-up of the system. We're operating the system. The Copernicus Sentinel satellites are operated by ESA. And the meteorology missions that are operated by EUMETSAT. So that's the essence of that infrastructure that I'm referring to. Of course, when we talk about capacity and assets from a European perspective, we should not forget that there's a huge fleet of commercial satellites by European operators, national missions, commercial missions that are contributing to the large volumes of Earth observation data and the large diversity of Earth observation data that we see today. Since in space, Europe is trying to establish a strong foothold in Earth observation, I should mention that in terms of the budgets that we have available for space activities in Europe, Earth observation is the only domain where Europe is actually at the same level as the US. The Earth observation budget, combined budget of the European Union, of the European Space Agency, is close to 2 billion euros per year. The value of the infrastructure, just in terms of the value of the satellites that you see here, so not to talk about the launch and the ground segments and the operations cost, is in the order of about 20 billion euros. So it's a sizable infrastructure that I'm referring here to. So that sets a bit the stage. In order to link a bit up with the theme that is developing here in this session, let me try to explain a little bit the evolution that we have seen in Earth observation over the last 10 years. 10 years ago, the Earth observation missions that we were operating, that we were handling, were characterized by still rather small data. We were collecting data in a very specific way that was supposed to make scientific communities happy, to make PI teams, scientific teams happy. And usually the data volumes were on the scale of a petabyte, perhaps over 10 years collected, maybe a little bit more, maybe less. We had few users in the hundreds or in the thousands. These were typically specialized users of specialized communities. We had no real fusion of what I would call the data industry. So Amazon and Google were not yet involved at the scale that we see today. The processing capacities, the transformation of data into information was still at a scale where there was no real industrial integration of Earth observation data. And from an ESA perspective, we also had a dedicated infrastructure. We were less relying on industry actually to provide everything as a service rather than having a dedicated infrastructure. So that was the characteristic profile 10 years ago. Now things have completely changed, and I have to say the game changer was Copernicus. The game changer was also a data policy, which is a free and open data policy for data of a resolution less than 5 meters. You see that the impact of that revolution in the fact that we now generating and disseminating data on a scale per day that we had over many years in the past. 10 years ago, a petabyte was disseminated in 10 years. Now we are basically disseminating a petabyte of data per day. We have, just by Copernicus, we have way over 50 million data products already generated. The number of users is counting in the hundreds of thousands. The Copernicus Sentinel Data Hub has 600,000 registered users. And that only constitutes, of course, the front line of the data access because it's free and open data. There are many, many entities, institutional entities, commercial entities that are contributing to the dissemination of Earth observation data. If you look into Google Earth today, you will also find Copernicus data as part of the Google Earth service offerings. What we also have seen is that rather than in the past where you had focused very specialized user communities, we have the full range of user communities. We have, of course, scientific communities. We have commercial users that are developing applications, services out of Earth observation data. And we have a very, very strong leg in the operational service domain where institutions are providing vital services to humanity in terms of utilizing on a regular basis Earth observation data. The availability of data in terms of timeliness, but also in terms of robustness of the systems and longevity of the data sources have become quite important. EO data has become a commodity of the data industry. It's clear that when you talk to large IT service providers, Earth observation data is often part of their standard offering of their services and products. Infrastructure and software have completely changed their appearance in the sense that industry is fully capable now, is mature to really provide end-to-end services in order to harness the data flows, to harness the data transformation into relevant information. And we are seeing a full integration of what I would call public and commercial data. I've mentioned already that there's these two domains of commercial data providers that are typically providing very high resolution data and the more institutional data sources, the satellites that are providing global coverage at lower resolution. And we have the concept of platforms. I will show you a few examples how platforms have changed the way that Earth observation is reaching out, is making an impact in the understanding of our environment and being able to manage the environment. Two key challenges that we see because the data volumes are increasing exponentially is we cannot afford to bring all the data to the users anymore. So we need to look for ways that we can bring the user to the data. The platforms are part of the solution here, but I will address a few other things here. And what we need to understand is even though we are investing and we are operating and getting ever more efficient in operating these Earth observation infrastructures, we still have to understand and we still have to optimize the way that we transform data into reliable and relevant information. The digital twin concept is a concept that is contributing to addressing that challenge as well. One thing that I've put here just to give you a bit of a physical sense what data volumes I'm talking about. If you would compress the data that is disseminated, the Earth observation data that is disseminated by ESA every day on high density disks, you would reach the size of the Eiffel Tower. That's the data volume that we are disseminating again as a frontline data access provider every day to the global community and to the large set of diverse users that I've mentioned here. So we are really talking about big data with all its relating challenges. Let me just show you a little bit what makes the essence of this new way of handling the infrastructure and the methodologies that we are applying. I've mentioned already that Copernicus was the game changer, and here is a good example of how European institutions can work hand in hand to really build up a system that makes a big difference. It's a co-funded program of the European Union and ESA. The European Union, the Commission, is the owner of the system, is defining the requirements, and our role is to be the system architects. We are developing the satellites. We are developing the ground segment elements, the processing, the acquisition of the data, all that needs to be handled on the ground, and the operations of the satellite. So I'm actually the person who's in charge of making sure that these satellites are doing what they're supposed to do. Here again, you see the figures. These are not the most current figures, but huge volumes of data being generated and downloaded. And again, free and open data is a key. One of the key elements that is now also emphasized in the further evolution of Copernicus, and we are already stepping into the next phase of Copernicus with a very much expanded fleet of new satellites, actually satellite families, that will fly very soon. The CO2 mission, hyperspectral missions, completely new types of measurements that will be used by Copernicus in the next few years to complement the existing system. But one of the key aspects is the ability and the efficiency to integrate commercial data, very high resolution data, in order to valorize and to enable services that have not been possible so far. Here the Commission and ESA are focusing in particular on new space companies, small companies that bring new ideas in addition to the established very high resolution data providers. And we see a lot of new technology, a lot of creativity and ingenuity coming from these new commercial entities that are springing up in Europe and globally. One of the key aspects that we are looking for when we look at merging and fusing data is really to make sure that the services that are at the core of the Copernicus system are being enabled to the maximum extent, and these are addressing key policies and key European issues in terms of the environment as well. I've already mentioned the impact that the establishment of platforms have had in the way that people work with Earth observation data. And at the beginning was the concept, I would say, of what we call the thematic exploitation platforms. These are platforms that are used by specific disciplines, by specific communities in order to address issues. Typical sizes were that you had a few thousand of these users on a platform in order to exchange data, to use calibration and validation methodologies, in order to use software for data processing, in order to communicate, in order to publish. These were at the origin of of these Earth observation thematic platforms that we have been developing. And you see a few themes here: seismology, volcanology, landslides, subsidence, floods, fire, urban development. These were the themes that were addressed in that systematic approach. And then we are talking about something quite current. This is basically the next step in the logic, how you actually manage and organize this huge global Earth observation infrastructure. Together with our friends and colleagues at NASA, we are developing something that we call the multi-mission algorithm and analysis platform. It's a very technical description for something that is actually changing really the way that users are interacting with Earth observation data of new missions. And we are implementing this as we speak. Prototypes of these platforms are running for the new Earth observation missions of NASA and the European Space Agency. We have selected the biomass mission of ESA, which is supposed to launch in 1.5 years, and NASA, which is a radar mission to be launched by NASA in a similar time frame. And what this platform actually is intended to do, based on a joint development and implementation, to bring diverse data sets from the satellites, but also complementary data together in such an environment. Use also airborne data, in situ data, and data products. Combine this with the computing capabilities and a set of tools and algorithms that support this research in this particular domain. So that should ensure that users are able to collaborate across the platform and to access the needed resources. Something that is actually replacing a lot of the functions that traditional ground segments in Earth observation were specifically developed to do in a virtual environment of cooperation. If you think and extrapolate the logic a little bit of what this means, you can see that for the user actually in a domain, it becomes completely transparent who's actually generating the data, what satellites are run by which agency is not so important anymore. And if you think a bit further, and we are doing that with our NASA friends already, these are missions that are actually operating in parallel, but you can actually define Earth observation programs now that are separated in time. So we are launching the EarthCare mission very soon, and a complementary mission of NASA will follow a few years later. Again, with such a virtual environment, a platform that is basically linking in terms of the data space, in terms of the usage, you can actually harmonize, synchronize Earth observation programs across the agencies. And this is a huge potential. It's actually going one step further now. We are also thinking really about how to integrate different disciplines. We are realizing that data, for example, from our science directorates in NASA and in Earth observation, for example, the heliospheric domain is relevant for some of the aspects that we do in Earth observation. So you can actually spread out in terms of these disciplines. And then finally, as a final example of how the way of cooperating and utilizing different competences and emphasis in technology in order to generate a new ecosystem. I use the example here of Destination Earth, which is a European Commission initiative for the development of digital twin Earth on an operational basis. So we are not talking about a research project here, we are talking about an operational system to support decision-making for important policy decisions, in particular in the context of European Union policies. And you see that together with the European Center for Medium-Range Weather Forecast and with our colleagues of EUMETSAT, who are the experts on the meteorology aspects, we are developing this system on behalf of the European Union. And we have distributed tasks. Here you see that ECMWF is taking care of the digital twin engine. The core service platform is integrated, so the integration part of all of this is with us. And the data lake, in particular, managing the output of such a huge system, which again will raise the order of magnitude of data volumes immediately compared to what I've been describing before. Clearly, new technologies, expanded use of cloud infrastructures, high-performance computing infrastructure, harmonized data lakes. We need to harness the Earth simulation and observation center competences. We need to harness AI and machine learning competences. And we need to make sure that the right data gets to the right places. So we need to rely on good networks, data networks that are capable on an operational basis, and I'm really stressing the operational nature and ambition of such a system. So that brings me to my last slide, which is just listing, again, maybe mapping a little bit on the typology and the differences that you've seen from the past to the future over the last 10 years in Earth observation. Clearly, the data policies have a huge impact, probably the key impact on the way that Earth observation data is penetrating society, is penetrating our ability to interact with the environment and understand the environment, the impact of the environment. The aspect of data integration is listed here. We see a lot of data integration methods actually being taken from domains that we didn't expect to be the drivers for this. The social media domain is one of these domains. Then we see the concept of the cloud and platform-based data access that I've just elaborated on a bit, and the aspects of data fusion with the ambition to take Earth observation data, which is much more than just imaging. I think that's a notion that I'm always struggling to bring across, that Earth observation is so much more than imaging. It's physical and chemical properties of the Earth measured at all scales and in very different ways, together from being able to understand the current status of the planet towards a predictive Earth observation approach, which of course relies on developing models, relies on a constant flow of data towards developing these scenarios. And I hope with this I've made a bit the case that this links very nicely up with the other presentation. Thank you very much.
Thanks a lot. Now we move to the last speaker, Sanna SORVARI SUNDET, Vice President, Research Infrastructure Services Unit at the Natural Resource Institute in Finland.
Thank you. And I also, good morning to everyone, and I also want to thank the organizers about the excellent organization of this session, because I think that we are really nicely complementing each other's talks, as you said, Nicolaus. Because today what I will talk is about the service perspective in the field of European research infrastructures in the field of environment. So mainly the ground-based environmental research infrastructures in Europe, and how we can then contribute to tackle the environmental challenges. So, but I really want to also to emphasize the service aspect. So as we have today talked, and already yesterday's plenary, it was really well established that we know that there is a human systems and ecosystems, they are in pressure. We have all the components and the pillars of the sustainability that we are working in all our fields, whether it is an ocean or whether it is an satellite related Earth observations, or whether it is related to diseases. So we are all working on these global challenges. And as you know, that there's many aspects of these global challenges, starting from the economic welfare up to the population growth and security of supplies in the societal side. But at the same time, there is a very traditional ones that we are normally used to tackle with environmental pollution, climate change, biodiversity. But at the same time, there are more and more topics raising from the food and water supply and the security, energy crisis, and the scarcity of natural resources. And I think that how we are tackling and how we should in the environmental field to tackle is to take care of all these aspects on the left-hand side. So the environmental research infrastructure approach has been that we are considering that the whole Earth is our laboratory. So it is that the Earth system science is behind there, where there was a really nicely demonstrated in the previous presentations an aspect of the marine systems, how we are tackling that part of the Earth system, or whether we are observing it from the space. But our contribution is really coming from the ground-based observations and so forth. And really to understand, so what kind of a research infrastructure services then this community can provide, it is, the organization started something like 15 years ago, very discipline orientation. So there was a research infrastructures based on some specific discipline, like whether it was atmospheric research or whether it was ocean related topics. Then there was more and more coming thematically orientated research infrastructures like themes around biodiversity or carbon observations or so on. And that is, of course, has an impact how we are providing our services, because there is this history of organization of our science disciplines. But I also want to highlight that something behind the service provision is also what kind of observations or experiments or models we are using. So this is the kind of the basics of all the service provision. So what has been always the core and should be also in the future, that we are taking care of the RI-specific service provision. So we are taking care of our own core user communities, those which are close to our science communities. We should never forget that basic role that we have. But in addition to that, we have to also to understand that the societal challenges or societal demands are not anymore functioning like that. So there is more and more coming more pressure how we are also providing our services. So therefore it is also very important that we have the interactions and operability with the different our core kind of players in the field, and also that we are connected to the operational services which ESA is, for example, providing, and whether we have a Copernicus or EOSFRI related topics. So we have to understand that. But what this is then about is that we understand that there is more and more these multiple and simultaneous and conflicting pressures. There is a complex and compound and cascading risks, and how we are answering to those kind of questions as a research infrastructures. And I think that this is where we are now. We are really tackling that what type of integrated service provision we can do, which is more agile for challenge and demand-based services, without forgetting our core user communities. So here's a couple of examples. So about the climate change and the carbon, I mean that very traditional work which is very important for the society. For example, that in ICOS, how they are providing biogenic carbon fluxes over the European land ecosystems, in this case in 2021, so that there is a compilation of the observations, models, and also for work done with the inventories, and this all work is then integrated for the service for the society. And I don't go into the details about the picture, but it is the most important is that there is this kind of a service provision for the society done by the ground-based research infrastructures in Europe. Of course, we are in a international conference where we should really always remember this global aspect. And in this field, for example, there are work towards global observation systems. And I know that this has been done now, has been worked under the WMO, so the World Meteorological Organization, and I'm pretty certain that our remote sensing communities are closely working with these kind of initiatives. So as we know, we need to have a science-based systematic observations, and this observational data and modeling has to be complementing the inventories, and we should not only focus on CO2, but it's also three other, that is the whole three major fluxes that we have and greenhouse gases. So this is just to demonstrate the kind of a business as usual work that we are doing at the field of environmental research infrastructures in Europe. There would be many, many cases in the field of marine or biosphere and terrestrial ecosystems. So I just gave one example. But when we are talking about these challenges, which are more multiple and more global challenges related to different themes, it is about that how we are building these common RI services and what is the techniques behind. So in the environmental research infrastructure community called ESFRI, there has been work since 2008 to 2009, and I think that this community has worked very well meeting these challenges what are faced, and also the demands for the research infrastructures over the years. So if you think about the service provision in the data point of view, for example, in the ESFRI FAIR concept, there are many data portals organized through these research infrastructures in Europe. They are serving many thousands, tens of thousands of users in their own domains. And there's plenty of suppliers, so the data provision suppliers. So that now thinking about that how to tackle all these challenges, and is this an easy kind of landscape for user to start organizing their research questions around, we have made it the world a little bit easier. For example, in relation to operational services, how we are communicating with the Copernicus services is that there is currently the direct access through each of the RIs can work, it's working, but we can question whether it is the most efficient way or is it easiest for the Copernicus collaboration, or are we then actually having a subdomain related data sets and service provision for also for our scientific and also for operational service, the needs for the different services. So the ESFRI community is now working to have an integrated access to these research infrastructure data assets by ESFRI FAIR and calling it as an ESFRI hub, which is then a communication towards the Copernicus as a whole, not only one subdomain services, but also for the European Open Science Clouds and all the other initiatives to come. One of the ones which has been nicely demonstrated several times, and I was kind of assuming that our colleague from ESA will talk more about the Destination Earth. So I will just only highlight that in the field of research infrastructures in Europe, there is already a contribution to 3 different digital twins and those projects, and I'm pretty certain there will be more to come in the following years. And therefore, I want to just to give a message that the research infrastructure are core contributors also to these initiatives together with the remote sensing communities. So there is this very important standard service provision that I think that we are all already very well established, and we can really argue that we are providing needed societal services. But also what I am very happy to see that there is more and more these fast response services to society. If you think about the world 10 years ago, around when there was the Icelandic volcano eruption, and how we were able to already that time to serve the society by right information related to ash plume and that related work. But it took still weeks and months to go. Many of the airplanes were standing quite a long time on the ground because this information was not there immediately. So what has happened in 10 years, I would say that this was the test. So when the Nord Stream leak was observed in 27th of September in the Baltic Sea, it was immediately like a half a day later, the ICOS observational sites were observing these peaks. The data was immediately harmonized and standardized. It was near real-time data. It was available openly through the Carbon portal to all the societal users to have a more understanding about the size of the plume, the impacts of this leakage, and so on. So what was there? In a couple of days, there was an understanding of the development and the transport of the plume across the Norway, Sweden, and all the way up to Arctic. There was an estimation and volume of the actual emissions in the plume, which was using the ICRI data, inverse modeling. There was at the same time also remote sensing initiatives, which were very nicely to be compared then, that whether this kind of an model work is compatible. And as we can say about this, that the results are saying that there was around, which is very difficult to estimate the real actual volume of the emissions, but there are something between 56 to 155,000 tons of methane was released in this leakage, which is a huge, never earlier seen one spot leakage. But at the same time, when you are thinking about the whole overall methane emissions in a year, it is a really small in that scale. But I'm just wanting to highlight that I think that we have come pretty far from in 10 years to have a societal services in a very fast response. So I think that this is because there was a harmonized and standardized data with the open data policy and with the data open API access. Okay, one of the questions that was also addressed to our this session was about the resilience of the research infrastructures and what is the sustainability, which is always an issue. And I was just a little bit worried, and we can also continue the discussion in the panel, that, for example, in the satellite data, there is a lot of services which the whole society and the industries are relying. What would happen if ESA would suddenly collapse? I mean, let's think about it. I mean, that we are already so important players in the field, so that many industries in the society would not be having any reasons, the means to cope, which is an excellent that we have been able to really to provide the services, but at the same time we have to understand that we have a huge responsibility in the society to really to keep industries up and running. So what I'm seeing it as a tool for resilience, at least in the research infrastructures which are distributed, they are still very much the assets lies in the research performing organization level. So it's really important to have a constant dialogue about that, what is the condition and the strategies of the research performing organizations, that they are having the resources to support these our societal services. And also that we have at the institutional and also the national level all the preparedness and the consistency plans ready for whatever kind of situations which we have now faced during the COVID-19 and also for this war situation in Europe. So that means that we have to have our research infrastructures business plans, but at the same time the agility to change as in these fast response services. So these are my main messages now, and I want to just to have a couple of take-home messages here to say that the global networks and RIs are needed. Our environmental research infrastructures are working together with the operational service providers, and without environmental research infrastructures and their resources and services, they would not be a solution to the societal challenges. Environmental research infrastructures has collaborated more than 10 years, and I think that we have been able to show our capabilities for these fast response services. Thank you.
Thanks a lot, Sanna. Thanks to all the speakers. I would like to invite you to come to the panel discussion. Yeah, we're a bit longer, but I mean, I was not able to stop these wonderful talks. It took me 30 years, just a personal comments, to see Isa saying such kind of thing. I'm so happy about this. So I cannot stop that. Okay, by the way, I mean, I think that we have touched a different aspect. We started from health issue, and now health and environment are related, which is very important aspect. I like the idea that you mentioned this, the exposome like an operational definition, because, you know, I'm not from that field. I think that we need to start to really work together between different disciplines, yeah. And now, just because in the order, all the data, or everything, it's from the satellite and Copernicus, which is a big program in EU. Canada, the ocean, I mean, and also the links with the European research infrastructures I've seen again, and all the environmental research infrastructures in Europe. I see that we have touched all the main points that we had in these sessions, which are related to, you know, the responsibility. Sanna mentioned that. It's, of course, in working in this field, we know that the citizens also, I mean, the society is waiting for information because the awareness is in. So this is an important aspect. I would like to, I don't know, if you want to comment more on that.
Yeah, it's something that I've noticed over the past several years. I had a conversation with Marcia McNutt, who's now the president of the U.S. National Academy of Sciences, back when she was editor of the journal Science. And her observation on the work we were doing in exposomics was that she saw this challenge is that what you're working on doesn't fit squarely within the National Institutes of Health, and it doesn't really fit in the National Science Foundation. And you're kind of in the middle. And it was just all the things that we were hearing about this morning. I'm thinking, we know that these things impact health, but we're not studying that connection very well. And I think this is one of these opportunities to look at how we can get better collaborations among these agencies, because you know, that dynamic between the health of the planet and the health of the human species is very critical in all species. But it is something where our systems aren't designed to study that interface, which is very important.
Maybe just to illustrate a bit this aspect of why are things coming together the way they seem to come together now. Just the way that we have been interacting within our disciplines has completely changed, and I just need to go through my file of contacts. 10 years ago, I was talking to space companies, space industry, to scientists in the space domain. The list of prime contacts has completely changed. I'm now talking to the IT industry. I'm now talking to disciplines that I didn't even know exist. So what I'm seeing here is a interdisciplinary way of working across boundaries. And I think these communities have been realizing, I come from the astrophysics community, so I know what a close community looks like. But there was always the sense of there is something to be gained in breaking down barriers. And I'm happy to see that this comes from the infrastructure side now, which is a bit unexpected, to be honest. I mean, I was always focused on the infrastructures. But again, being quickly able to relate to what is said about the medical sector and ocean science, and seeing the relevance of this for my own domain gives me a warm feeling, which compensates a bit for the threat of being exposed. And
well, I will certainly follow in the footsteps of the two predecessor interveners here, to say that research infrastructures have usually hidden capabilities to foster transdisciplinary. And sometimes they don't realize it. We want to address the needs of the biologist and then the needs of the geophysicist. But then you can look at it from across, like draw a horizontal line among all these disciplines, and indeed you can sometimes serve them, and that's how you discover new potential. And I would go even further than that. I mean, one of the things that we're trying to do at Ocean Works Canada as well is to support, well, the social sciences, but also the humanities. I mean, having an inspiration that the discoveries we're doing on the science side, that the services that we're rendering to the public and the benefits we're trying to achieve for the planet can become an inspiration for artists as well. So we've got an artist in residence program at our research infrastructure as well. So you can broaden the scope to cover so many different topics.
I would also come back to the data. I think that this data policies has been really the revolutionary here. I think that without opening the data for everyone and making it really easy access, I mean that's the cornerstone for the interdisciplinary and the transdisciplinary work. And I think that this is now where we are facing, that we are data providers for the really wide communities, and we would never ever in the first place kind of dream that who would be the users of the whole user communities or of our data. So I really want to highlight that I think that has revolutionized the whole system.
Yes, we have spoken about this kind of social aspect and what we are able to produce now, and but we are also protagonists of our future and of the next developments. And in this direction, my last question to all of you is really the role of research infrastructures to solve the issues of the borders among different disciplines, but also among different countries. We have seen this, in some sense, the Earth observation program from ESA and NASA for me are exactly research infrastructures. I see them in the same way. So what is the role and how we can use this, I mean, we probably should improve the visibility of what we are doing as a research infrastructures, the example that we have with Europe and US, with Canada, and to build on that. I think this is something that probably we should use more than what we've done so far. Yeah.
I think that we have proceeded a lot in global collaboration, and I think that one of the reasons for that is that we have to do our own homework. So we have to be well-structured, organized, in order to be easy partner for this global cooperation. So I think that if we are, in a way, I'm always saying that we should take care of our own and handling our own business well. So because that then helps the collaboration, and of course when we are working to organize everything in a harmony and a harmonized and standardized ways, of course that is the key for this collaboration and our own responsibility of doing our things well.
Yeah, and making sure that we're complementary rather than competing, for
exactly.
sure. And certainly the example that Nicolaus highlighted with the MAP program between NASA and ESA is certainly a great example there. But there's many others. There's many others where interoperability, agreements on data formats and data exchange mechanisms, agreement on data quality and metadata are making all these potential for growth and across research infrastructure capabilities more viable. And so I think we need to continue there. I think we made a good progress in the last couple of decades, but there's still some work to be done to achieve that ideal situation, though we have great examples that are already happening.
Just two thoughts from my side. Open data, I think, is a key element, but it's not the end. I think open resource, open software, open processes in general, up to the publication process, I think is a key question here. Reproducibility, transparency, these are the key ingredients. And I have to come back on this resilience aspect because I was wondering why I had a good night's sleep and maybe I shouldn't have. But I think a key element in all of this is also industry. We need to make sure that the industrial capabilities and the way that industry is interacting with the institutions and developing their solutions for what we are trying to achieve are also part of this. And this is where the resilience comes from. That will be my response. The systems and services are not proprietary systems anymore, and here industry can help a lot.
One of the things that I've found, I've been a bit jealous of this, and looking at these other agencies and infrastructures, is how well the data are shared. When you work with human data, we have privacy protections and things that often, I think it makes it easy for people to think, well, we can't share the data because of the privacy, and not focusing on how to do the right de-identification so we can extract the data that maintains privacy, but I mean, that's the thing, like, you know, we have 8 billion people on the earth that are essentially all sentinels of all of these changes. But when we hide behind the privacy protections, which are important, we need those, but I think there are ways of doing better de-identifications. We can get that out of there.
Absolutely, this is a great message, and we need that. Okay, so I think we have still 5-6 minutes, so I will give probably 2 minutes or 1.5 minutes each for the last message to leave to the audience, until we don't have specific questions from the audience. We have. Okay. Okay. So no, just good.
Thank you. I'm Frédéric Sgar from the OECD Global Science Forum. I had 2 short questions. The first one is related to MAP. And I was wondering whether we could go one step further in having a sort of a common data access platform for the users, or what are the challenges to go, that way, beyond just having a common analysis system. And the second one is for Sanna, is regarding the contingency planning and the robustness of the system. I think we all agree that during the COVID-19, it was sort of a real-life crash test for many research infrastructures. Do you have examples, concrete examples of research infrastructure that actually have stepped up their contingency planning, and in what way?
You first? Yeah, well, I mean, yes, okay, I can take the second question. I mean, honestly, I don't know. I mean, that in a way that I think that it was really tackled at the national level, because there was a lot of, take Europe. I mean that the situation was not the same at the same time everywhere, and also how the institutes were responding and national response was different. So I think that this is really a place where we have to work a lot in the future, and I think that this was a really a call for all of us, that this consistency plans has to be in place. But how to then to integrate the different national and research performing organization level different ways of handling it. I think that that's our future task.
And on the data access, the story is a bit complicated, I'm afraid. Of course, data access, common data access is something to be easily implemented. Just to give you an example, the #1 Earth observation data product disseminated by NASA is actually Copernicus Sentinel-1. So the data access is basically already completely distributed in that sense. The problem that we see a little bit, we are losing two things by pushing that without indiscriminately. The first thing is with free and open data, you have so many opportunities to access the data, it becomes difficult for the user sometimes to evaluate the reliability of the data source. Some of the data that is offered is not authentic data. You don't know whether the data will be there tomorrow. You don't know about the quality of the data, the timeliness of the data. So it becomes a question of how to assure a certain level of trust that goes with accessing the data. I think that's an important aspect. And what we also see, of course, a free and open data policy only makes sense if you lower the barriers of accessing the data. So user registration, for example, was always a big topic. We have lowered the barriers to a level where usually we are only asking email addresses now. But of course, we are losing a lot of information about who's actually using the data for what purpose. So that's another aspect. And especially when the data becomes critical and some of the data that we are talking about is politically relevant, we are entering a domain where things are becoming a bit more complex. That's why I'm making these statements.
Oh, I think, okay, 1, 2, 3, 4. Lukas was first. Okay.
Thank you so much. I'm Lukas Slovak from Czech Ministry handling the research infrastructure policy making here in Czechia. I have a question most probably for Gary. Well, considering all the amount of findings on the environmental exposure which affects the human health, how are you able to reach the regulatory authorities? Are you there yet? What's the level of your interface?
So in the United States, where we are, our National Institutes of Health does our research, and things like the Environmental Protection Agency does the regulation part, is we're still challenged at looking at very simple mixtures of chemicals. So like looking at a couple different types of pesticides. So the idea of like using an exposomic approach is still, they're grappling with this. And we've had several meetings with them, but the regulatory framework is not ready for a complex piece of it. And I'm really afraid it's going to force us to go back to this sort of one-by-one chemical. And we know it won't work, but that's what the framework is now. So there have been discussions, but I don't know what the solution is. We're just trying to drive the science forward, and hopefully the human-based science will force those changes in the regulatory structure, because they really don't have a good way of dealing with complex mixtures. So, fingers crossed, yes.
2, 3, and 4, very quick, because there is a coffee break waiting outside.
Okay, Alistair Reid, European FS Centre in Brussels. I have a question, picking up on the resilience question, and listening to you all, data is the big issue. And the obvious resilience thing that comes to my mind is how secure are all the systems and the data systems and so on. And it's probably a question that will take a lot longer than to answer than the coffee break, but it's something that struck me listening to you, so I just wanted to put that into the frame here.
Yeah, I think that the cybersecurity is a very important aspect nowadays for the data, and we really have understood that when we are talking about the scientific data or whether it is observations, there's always an issue that we have to take care of the cybersecurity, and I think that all the research infrastructures are currently working on it.
If you want to answer.
Maybe just a quick comment, because again, I think that the times are such that this is the #1 thought that everybody, and when I look at my phone, this is what I'm usually occupied with. But just to note what I said previously about openness, and there is a certain contradiction in in these statements, or maybe not. It's just something to think about, to really make the scientific and the data to information process transparent on one side, and on the other hand, to be resilient and cyber secure. We have to find ways to make it compatible. I think that's the key challenge.
Hello, good morning. My name is Juan Jodañovetia, and I'm from EMSO ERIC, Research Infrastructure. Everybody talk about data, about big data, about better data, but the question is, it is time to dive into the data clearly and to have a very excellent data and high quality control. And I have a specific 2 questions for Nicolaus and for Benoît. you talk about very high resolution data. I don't know what is the diving of the satellite, you decrease the altitude or whatsoever. And for you, Benoît, you have an incredible, huge system based on cable observatories and standalone observatories, which is completely different sample rate and very complicated to merge this type of data, because you were talking about interoperability, the only one in the whole. And I think interoperability is the key point to have multidisciplinary access to different type of data, because then we understand each other. Sorry.
Yeah, I'm not sure it was really a question, more than a statement that you just made, but yes, typically what you want to do if you have data from different sources that you want to be able to use together and combine perhaps in a transdisciplinary manner, what you need to do is to use time. Time is your index. And so that's what makes things really important, that you have a good understanding of when things were captured, obtained, acquired. So that would be an important thing.
And just on the logic of very high resolution data, so the commercial domain is covering for that very high resolution aspect to a large extent. Not only the defense sector certainly has also its assets. It's an operational issue in the end. If you have a high resolution satellite, these days implying something at the scale of 20 centimeter resolution on ground, then you need to know where you want to look and what to analyze, whereas our missions are larger or covering a larger area. But it fits nicely, and the message here is that the commercial and institutional sector are depending on each other and appreciating each other. That wasn't clear, and it comes back to the question of the data policy. At the beginning, there was actually resistance, especially by the commercial sector, selling very high resolution data for a free and open data policy. This has been overcome, and now I think 95% of the commercial companies have recognized that this global lower resolution data is providing an excellent reference in terms of the data itself, but also in terms of the applications. So that's the secret, and it fell into place.
My name is Enzo Caparone from Géant. I have a question about the sustainability of the infrastructure. I'm specifically thinking about the Copernicus program, that even now it has a huge amount of data, like literally huge. And we know that the most critical aspect in a digital infrastructure is, well, it used to be the total cost of ownership of storage. Now it's also the energy bill, but let's not talk about that. And even now, the data is increasingly, in a geometric way. And with the new satellites and probably the byproducts of destination Earth, it's only going to get worse. Does ESA have a long-term strategy for tackling this specific problem, the sustainability of the storage cost?
Yeah. First of all, and again, it comes to resilience, to the resilience questions. We have just been signing the contributing agreement with the European Union on the Copernicus phase 2. So we know exactly what to do for the next 5 to 6 years, which satellites to build and how to evolve the ground segment. The good news is that technically we have been successful to transform the ground segment, the data management part, in a way that even though the data volumes are increasing exponentially, the cost is actually linear. We are spending exactly the same amount of money today as we have spent 6 years ago for the data management part. So that gives us a bit of confidence that we are technologically innovative enough to deal with this. One of the key things, and that's the discussion that we're having here, is we are realizing something that I didn't know 3 years ago, that high-performance computing, the capacities that are usually focused on research activities, can be harnessed also for operational purposes. So what we are looking now at is using research-focused capacities to operationalize them and making them part of the resilience, the sustainable resilience of Copernicus. So that's a large part of our evolutionary program. Cloudification was a big step forward. Everything is on the cloud now. The next step will be the processing in HPC environments, just as a very simplified answer.
Thank you.
Thanks a lot. I think it was a great session. Thanks to all the speakers and also to the audience for the active participation. Thanks a lot and enjoy the coffee.